Welcome back to LectureCast-SMT. In episode 1 we set up a courtroom, the language model argues, and the solver rules. Today we go inside the judge's head. How does a solver actually decide whether thousands of interlocking rules can hold together, in milliseconds, with a proof attached? I promised you an episode with 0 formulas, and I will keep that promise. Everything you are about to hear arrives as a story, a puzzle, or a picture. By the end, the word satisfiability will feel less like jargon and more like the name of a very particular kind of detective work. A ruling you cannot understand is hard to trust, and this whole series is about trust. So before we write a single line of code, we will answer 3 questions. First, what kind of question does a solver actually answer? It is narrower than you might think, and that narrowness is its superpower. Second, how does it search a space of possibilities that is, quite literally, astronomically large, and still come back in milliseconds? And third, the question that matters most for agents: what happens when the answer is no? To keep everything concrete, we will carry one running example through the episode, a tiny staff roster. Small enough to solve in your head, and, as you will see, rich enough to break in an instructive way. And if you take away only one idea today, let it be this: a solver is not fast because it guesses well. It is fast because it learns from every dead end. Here is the puzzle. 3 staff members, Alice, Ben, and Chloe. 2 shifts on Saturday, a morning and an evening, and each shift needs exactly 2 people. For house rules. Rule 1, Alice and Ben do not get along, so they never share a shift. Rule 2, Chloe has childcare in the afternoons, so she works mornings only. Rule 3, every shift is staffed by exactly 2 people, no more, no fewer. Rule 4, nobody works both shifts in one day. The question sounds almost trivial: does a valid roster exist? Now notice something about the shape of this puzzle. Every decision in it is a yes or a no. Does Alice work the morning shift, yes or no? Does Chloe work the evening, yes or no? 6 little switches in total, plus rules connecting them. That is the entire world as a SAT solver sees it: switches and rules. Nothing else. Satisfiability is the solver's one and only question: is there any way to set every switch so that every rule is respected, all at the same time? Not what is likely. Not what is typical. Just, can all of this hold at once? 2 answers are possible, and both are more valuable than they first appear. If the answer is yes, the solver does not just say yes. It hands you a witness, a complete, concrete assignment of every switch. A roster you could pin to the wall. Let us try to build one ourselves. Chloe can only work mornings, so put her in the morning. The morning needs 2, so add Alice, say. Fine so far. Now the evening also needs 2, and only Ben is left. 1 person, 2 chairs. Try swapping, put Ben in the morning instead. Now Alice and Chloe must cover the evening, but Chloe cannot work evenings. Stuck again. And if the answer is no, it is not the solver shrugging. Unsat means no assignment can exist, provably. Our little roster, as you have just felt in your own hands, is exactly that, unsat. The rest of the episode is about how a machine discovers this, and how it explains itself. So how does a solver find this out without trying every combination? It works the way a good detective works. Watch the method in slow motion. Step 1, assume. The solver tentatively flips one switch. Say, Alice works the morning. Step 2, propagate. It instantly chases every forced consequence. Rule 1 now forces Ben out of that morning. Rule 3 then forces Chloe in. One assumption, and a cascade of automatic deductions follows for free. Step 3, collide. Sooner or later, some rule breaks. And here is the mental shift that matters. To a solver, a contradiction is not failure. It is evidence. Step 4, the crucial one, diagnose and learn. The solver traces the collision back to the handful of assumptions that actually caused it, and records the lesson permanently, never that combination again, anywhere, ever. Step 5, backtrack smart. Not all the way to the start, only as far as the diagnosis demands, keeping everything else intact. Then it repeats. Eliminate the impossible, as a certain detective liked to say, and whatever remains must be the truth. Let me show you why step 4, the learning step, is the whole story. Our toy roster had 6 switches, so 64 combinations. Brute force would be fine. But scale up just a little. 300 yes-no switches allow more combinations than there are atoms in the observable universe. And real problems, the ones C3 chews through daily, involve not hundreds but millions of variables. No amount of raw speed survives numbers like that. If solvers merely tried possibilities faster, they would still be running when the sun burns out. The trick is not speed. It is memory. Every contradiction the solver hits becomes a learned rule, added to its own rulebook. And a single lesson can be devastatingly general. It does not say that particular path failed. It says every future containing this pattern must fail, and billions of branches vanish at a stroke, unexplored. The search space shrinks faster than the solver walks it. That is the entire miracle. It is also, I think, why watching a solver work feels uncannily like watching something think. So that is SAT, a detective for worlds made of yes-no switches. Brilliant. But now listen to the constraints real agents face, the ones from episode 1. The shift ends 8 hours after it starts. Total pay for the shift must not exceed $400. No staff member can be in 2 wards at once. Do you hear the problem? These are not switches. They are statements about quantities, about time, about money, about relationships between people and places. In principle, you could grind numbers down into thousands of individual bits and feed them to a pure SAT solver, and for some domains people genuinely do. But for the kind of reasoning agents need, the encoding explodes, and worse, the meaning disappears. The solver would be pushing bits around with no idea it was ever talking about dollars or hours. What we want is a detective who can read the ledger, not just flip the light switches. We want logic that speaks number natively. And that brings us, at last, to the letter M. SMT stands for satisfiability modulo theories, and the word modulo simply means, with respect to some extra background knowledge. Picture the architecture. At the center sits the same relentless detective we just met, the SAT core, managing the yes-no skeleton of the problem, which constraints are switched on, which combinations have been ruled out. But arranged around it is a panel of expert consultants, one per theory. An arithmetic expert who genuinely understands integers and real numbers, so it can tell at a glance whether 8 hours at these rates can stay under that cap. An array expert for indexed collections like schedules and inventories. A function expert for relations, who reports to whom, what maps to what. And more theories plug in as needed, bit vectors, strings, sets. The engine and the experts interrogate the problem together. Whenever the logical skeleton mentions numbers, the engine consults the arithmetic expert. The expert either blesses the current picture or reports its own kind of contradiction, which the engine then learns from, exactly as before. The verdict at the end is joint. And, crucially, it is still a proof. Now we can upgrade our puzzle with numbers, and meet the idea that makes this whole series practical. 3 clauses, taken straight from the world we will enter properly in episode 4. Rule 1, casual staff receive a 25% loading on the base rate. Rule 2, total pay for a weekend shift must not exceed $400. Rule 3, a weekend shift runs at least 8 hours, and the base rate is $42 an hour. Each clause sounds perfectly reasonable on its own. Ask C3 whether they can coexist, and the arithmetic expert does the sums. 8 hours, at $42, with the loading, comes to $420. The cap says 400. Unsat. But here is the gift. Z3 does not just say no. It returns the unsat core, the minimal set of clauses that cannot coexist. Watch what the core really claims. Here it names all 3, and minimal means exactly that. Remove any one clause, any one, and the conflict vanishes. So the core is not a vague complaint. It is a written judgment with the guilty clauses named. In episode 4 we will run precisely this kind of check on real award rules, in real code. Step back and look at what we now have. Every ruling this judge hands down comes with receipts. A yes arrives with a witness, a concrete solution you can execute immediately and that anyone can check in seconds. A no arrives with a core, a proof of impossibility plus the minimal list of clauses to blame, which is exactly what turns an agent's veto from arbitrary into auditable. And sometimes the solver runs out of time or memory and says unknown, honestly. That third verdict is not a flaw, it is a budget, and good engineering decides in advance what happens then, retry with more time, relax a constraint, or escalate to a human. And underneath all 3 verdicts sits a property that no language model can offer you. Same input, same verdict, every time. Deterministic, replayable, citable. When your agent refuses to execute an action, you can rerun the exact check, point at the exact clauses, and file the exact proof. That is the difference between a veto you can audit and a vibe you must trust. 3 ideas to carry forward. 1. Solving is learning. The solver conquers astronomical spaces not by guessing well but by converting every dead end into a permanent lesson that prunes billions of futures at once. 2. Theories give logic its number sense. SMT is the detective plus a panel of experts, and that combination speaks the language agents actually need: money, time, quantities, relations. 3. With a solver, no comes with names. The unsat core turns rejection into explanation, and explanation is what makes automation trustworthy. Next time the training wheels come off, just slightly, episode 3 is Z3 in 10 constructs. Our first real code, and the complete working vocabulary you will need for every case study that follows. 10 small pieces, each in 20 lines or fewer. If you have never written a line of Python, come anyway. You will be surprised how far the intuition from today carries you. See you then.